In this lesson, we'll talk about full-text search. Full-text search is the technology behind the billion-dollar search engine industry. Operating systems these days also provide tools to search local files, and of course, it's also widely used in web applications. For example, web forums let you search for posts. News websites let you search for news stories. Online retailers let you search for products based on product descriptions and so on. At this point, you may be thinking why we are talking about some full-text search technology when we already know how to search text using SQL. For example, let's say that we want to search a web forum for some posts that contain the words SSHD login errors. Suppose the posts are stored in a database table called posts, and suppose the content of the post is stored in the column content. We can write a query like this. We can say select star from posts where content like, and this pattern. Note that here we use the SQL operator like, which checks if content matches this pattern. The percentage symbol here in this pattern represents 0 or more characters. So the pattern basically checks if the words SSHD login errors appear anywhere in the content. If we run this query, we'll get results like this, and the whole thing seems to work fine. So what's the problem here? Why do we need to learn some new thing called full-text search instead of just using SQL? Well, there are two problems here. The first one is obvious. If we look at posts like this, we can see that they are most likely relevant to what the user is looking for, so they should be in the results. But our SQL query will not find this post for various reasons. For example, because the three words are not adjacent to each other, or they are not in the right order, or because the words are slight variations of the query words, for example, error instead of errors. In other words, the first problem of this simple pattern matching is that it's likely to miss lots of useful results. The second problem, which is less obvious, has something to do with performance. Pattern matching is a fairly expensive operation, and it's particularly expensive when there's a wildcard symbol at the beginning of the pattern like this. The reason is that when you have a wildcard symbol at the beginning, pattern matching can no longer take advantage of database indexes like B-tree, so you'll have to search through all the data. For a large data set, a query like this will take forever. This is why people develop full-text search technology, which is also known as information retrieval. Unlike database technology, which is designed to support a number of operations like select, insert, update, and delete for various data types, full-text search is designed for a single purpose, to search lots of text very, very fast. There are a couple of important differences between full-text search queries and regular database queries. First is that FTS query processing is somewhat fuzzy in the sense that sometimes there's no definitive rule that decides whether a document should be included in the results. For example, if we search for SSHD login errors, should a post including 2 of the 3 query words be included in the result? How about a post that contains the word error instead of errors? The answers to these questions depend on the algorithms and settings you use. The second difference is that the results of a database query are all equal, as they all equally satisfy the search conditions. But full-text search results are not equal. In fact, there's usually a relevancy score associated with each full-text search result, which indicates how relevant that result is with respect to the query. This is particularly important for search engines, where a query can easily return millions of results. Nobody wants to browse through millions of results, so it's very important for the search engines to determine which results are the most relevant and put those results at the top of the list. Because of the way full-text search works, sometimes the results may contain documents that are not considered relevant to the query, and sometimes documents relevant to the query are not included in the results. So people came up with two measures called precision and recall to evaluate and compare full-text search algorithms. For application developers like us, it's also important to understand precision and recall because it lets us understand the trade-offs when we configure the settings of an FTS algorithm. Precision is defined as the number of relevant documents retrieved over the number of documents retrieved. Recall is defined as the number of relevant documents retrieved over the number of relevant documents. Now let's see some examples to understand what these two measures mean. So let's say I have 1,000 documents and I have a query, and among those 1,000 documents, let's say there are 200 documents that are relevant to the query, and let's say there are 300 documents returned as the results of the query, among which 100 of them are relevant. Okay, so 1,000 total documents, a query, and if we look at all those documents, 200 of them are relevant to the query, and because a full-text search algorithm may not be perfect, if the algorithm is perfect, of course the algorithm will return these 200 documents and only these 200 documents. But since FTS algorithms are are impossible to be perfect, let's say our algorithm returns 300 documents, and among those 300 documents, only 100 of them are actually relevant documents to this query. Okay, so given these numbers, if we look at the definitions of precision and recall, we can see that precision of that algorithm is 100, that's the number of relevant documents retrieved, over 300, that's the number of documents retrieved. So it's about 33%. And for recall, that's 100 number of relevant documents retrieved over 200, that's the number of relevant documents, and that gives us 50% of recall. So if you look at the results, you can see that recall and precision are two different measures, and they can be, in terms of the value, they can be quite different. And we can also look at a couple of extreme cases. For example, let's say in one extreme case, we say we have an algorithm that always returns all the documents, all 1,000 documents. So in terms of precision, it will be 20%, because we know that 200 documents are relevant, and if every time this algorithm always return all the documents is 200 over 1000, is 20%. However, recall, as you can see, is actually 100% because all the relevant documents are returned. So, as we can see, if we have a very high recall, it doesn't necessarily mean the algorithm is good, because the precision can be bad and the algorithm can be, in fact, very simplistic. The other opposite of an extreme case is, let's say we have a good algorithm, and this good algorithm only return one document, and this document is a relevant document. So one document returned and it's relevant. So in this case, the precision will be 100%, yet the recall is going to be only 0.5%. So as we can see, our algorithm can have perfect precision but really bad recall, or it could have perfect recall but really bad precision. So this is why we need both measures, and a good algorithm should have both high precision and high recall. Now let's see how full-text search works. There are two parts in full-text search. The first part is building an index of the documents, and the second part is searching the index to find the documents. This diagram shows the steps in building a full-text search index. Suppose we want to search for HTML pages. The first step is to take the original HTML document and strip it down to the text-only form like this. It's very important to understand that a full-text search algorithm only deals with text. Although search engines and search tools usually allow us to search different file types like PDF, Word, PowerPoint, and so on, those capabilities are not built into the core full-text search algorithm. Instead, you'll need additional libraries that convert different types of files to text, and then use a full-text search implementation to index and search them. Here are a few common file types and the libraries that can be used to convert them to plain text. You can find more information in the Lucene FAQ from question 28 to question 22 in the index section, which is here. So 28. So as you can see, it says how can I index HTML document. It lists some libraries that can be used to convert HTML to text, and similarly, there are information about converting XML documents, OpenOffice, Microsoft Office documents, emails, PDF files, JSP files, Java files, and so on. And let's look at a couple of examples. In the FTS example, there are a couple of programs. One program can extract text from Microsoft Word documents, and the other one can extract text from PDF documents. So, as mentioned here, for PDF files, we use this Apache PDF box library, and for Microsoft Word files, we use the Apache POE library. I should mention something about that dependency, those dependencies though. First, this is the dependency for PDF box. The group ID is org Apache PDF box, and artifact ID is PDF box. The thing I want to mention here is that if you use Eclipse to search for PDF box, you'll find it here, but notice that it says something about a bundle. If you select that dependency, Maven will give you an error because you are selecting something called a bundle, and we need to change that type to jar. So don't keep the original bundle type. Change that bundle type to jar, and that should fix it. The second thing about the dependency is that for the POE dependency, we actually need 3 of them, not just the POE, but also POE OOXML and the POE scratchpad. If I'm not mistaken, the POE OOXML package is needed to handle the newer versions of Microsoft Word format, like the docx, the files with the docx suffix, and the scratchpad is the one that handles older versions of the Word formats. So once you have those 4 dependencies, you can do the text extraction thing. The Lucene dependency is for something else, which Lucene, by the way, as we'll mention later, is a Java FTS library, but we no longer cover Lucene in the class, so you can safely ignore this dependency. Now, once we have the dependencies, it's actually quite easy to extract text from Word and PDF files. I have a couple of sample files here. The first one is a PDF file called sample1.pdf. You can see that it's basically the schedule of the final exams, and the code to extract text from that PDF file is this. As you can see, it's a very simple code. So the first line will locate the file on disk. So files is the folder name, and the sample1.pdf is the file name. So this one will create a file object, and then we load that file object into a PDF document object, and then we create something called a PDF text stripper, and this text stripper will extract the text from the PDF file. And to do that, we have to provide a writer, and the text stripper will write the extracted text to that writer. So here we are using a string writer, meaning that we want the extracted text to be stored in memory in a string. So we write the text into this string writer, and then from that string writer we take the final output text back, and then we print it out. So if we run this code, we can see that the final schedule text is printed out here. So the PDF file is converted to plain text. Doc2 text is similar and even simpler. So again, we first load the file, which is this one, sample2.docx. This again is a final schedule, but this one is in Word format. And after the file is loaded, we put it in something called a POE text extractor, and then the extractor simply extracts the text as a string. So it's even easier than PDF. We don't even have to go through a string writer, and then we print out the text. So if we run this, again, it prints out all all the text in the PDF in the Word file. So as we can see, once we know what library to use, it's fairly easy to take the text out of certain file types, and then after that we can index them, and then we can perform full text search on them. Okay, so the next step is to tokenize the text now that we have extracted them from the original file, whether it's XML or PDF or Word. And tokenization means that we want to break the document down into individual words like this. Depending on the language, tokenization can be relatively easy or it can be quite difficult. For English, it's relatively easy because there are delimiters like spaces between words. But for a language like Chinese, tokenization can be quite hard. For example, suppose we want to tokenize this sentence. If we don't know the language, there are two common ways to tokenize it. The first way is to simply break it down into individual characters, and this is called unigram tokenization. The second way is to group every two characters together to form a token. For example, we can say these two together is a token, and then the next two is a token, and the next two is a token, and the next two is a token, and the next two is a token. So this one is called bigram tokenization, and is based on the observation that the majority of Chinese words consist of two characters. But if we understand the language, or more accurately, if our algorithm understands the language, we can do a grammar-based tokenization, which would correctly break the sentence down into three words: 今天天气不错, which mean today, weather, not bad, or good. If you compare the three approaches, you can see that if we look for any of these three words, all three approaches can find it. For example, this word can be found here, and it can be found here, and this word can be found here, and can be found here. And this means that all three tokenization methods will have the same recall. However, both unigram and bigram will also match words that do not actually exist in this sentence. For example, the word 天天, which is actually a valid Chinese word meaning every day. This word actually does not exist in this sentence, but it appears here, and it also appears here, which means that if a user search for this word, these two tokenization methods will think that this sentence contains this word, and that means the precision will be less. The lesson here is that the tokenization algorithm can actually have a big impact on the overall performance of full text search. When you have multiple tokenization algorithms to choose from, be aware of the trade-offs they make regarding precision and recall. Okay, so the document is tokenized, and the next step is to remove the stop words. Stop words are function words like a, and, the, and so on. These words appear in virtually every document, and they don't have much meaning, so they are not very important for search. Usually we would want to remove those stop words, but this does cause some problems in some rare cases. For example, to be or not to be is a famous quote from Shakespeare's play Hamlet. Note that this code consists of entirely stop words. After performing stop words removal, users will not be able to find this code. In case you are curious, you can try Googling to be or not to be, and you can see that Google can find this without any problem. In fact, we can even search for A. Google will tell you that there are 25 billion something results, or the, and same 25 billion results approximately, I guess. So what this means is that Google doesn't do stop word removal, and obviously it has its advantages. But on the other hand, Google has hundreds of thousands of servers, if not more, so they can afford to index and search every word. But for systems with less resources, removing stop words is probably a good idea. After we remove the stop words, the next step is to do stemming, which means to reduce a word to its stem, or the root form of the word. As shown in this example, words like connection, connections, connected, connecting, connective, they can all be reduced to the root form or stem connect. Stemming is performed not only on the words in the documents, but also on the query words during search. The purpose of this is to improve recall. For example, if a user searches for the word connection, the result will include not only the documents that contain the word connection, but also the documents that contain the word connections, which are also likely to be relevant. On the other hand, we can see that documents containing things like connected, connective will also be in the results, which suggests that the stemming is probably bad for precision. Overall, it's probably better to do stemming because usually it's better to include too much than missing something useful. After stemming, we are finally ready to index the documents. The index is called inverted index, which looks like this. It's called inverted index because normally we would go from documents to words. But in inverted index, we go from words to documents. The first part of the index is a list of the words that appear in the documents. For each word, we maintain a bucket. And each entry in a bucket contains a pointer that points to a document that contains that word. An entry in a bucket may also contain some additional information about the word and the document. Exactly what those additional information is depends on the full-text search algorithm, but usually it includes the length of the document, the number of occurrences of the word in the document, the positions of the word in the documents, and so on. With an index like this, search becomes very, very efficient. For example, if we want to search for cat, we can easily locate cat in this list. And by the way, we can build additional index structures on top of this list. For example, we can use a hash index to index this list itself, so locating a word like cat in the list only takes constant time. Once we find the word, we immediately get all the documents that contain the word. As we can see, this is much, much faster than searching through each document and looking for the word cat. Similarly, if we want to search for both cat and dog, all we need to do is to locate both cat and dog, then do an intersection of their buckets to get the documents that contain both cat and dog. Inverted index is a very important technology in full-text search. Although actually implementing it for large-scale systems like a search engine is still tremendously difficult, conceptually it pretty much solved the search problem. This diagram shows how a full-text search query is processed. Noticing a query goes through a similar process like a document during indexing. In particular, it goes through tokenization, stop words removal, stemming, and searching is performed using an inverted index to locate the documents that contain the query words. And then, in the last step, which is very, very important, we need to rank the documents in the results. Anyone who has done web search knows a search can easily return thousands or even millions of results. Nobody wants to go through all the results to find what they are looking for. So it's very important for the search engines to rank the results properly, so what the user is looking for appear at or near the top of the list. So how is the ranking decided? Well, each result has a relevancy score, sometimes also called a similarity score, which indicates how relevant or similar a document is to a query. There are two general approaches for determining relevancy. One is based on how well the document matches a query, and the other is based on how important the document is, where the importance can be based on things like ratings or citations if the documents are academic papers, or links to a web page if the documents are web pages, and so on. Algorithms to calculate relevancy are outside the scope of this class. If you are interested, you can take a look at the similarity class in the Lucene library. Lucene is a very popular Java full-text search library. The documentation of the similarity class explains how Lucene calculates the similarity between a document and a query, which involves a number of factors. Factors like number of times a term appears in a document, number of documents that contain the term, number of query terms found, and so on. As I mentioned, and as you can probably tell by reading the documentation, relevancy calculation algorithms are very complex, and usually you'll find more details about those type of algorithms in a class that discuss specifically about information retrieval. For us, we just need to know some basics, and the more important things for us is how to incorporate the full-text search into web applications. And when it comes to that, we have two choices. We can choose to use the full-text search capabilities provided by database management systems, or we can choose a standalone full-text search library like Lucene. Generally speaking, full-text search provided by database management systems is easier to use because they are implemented as extensions of SQL. If you already know SQL, it's very easy to learn how to do full-text search. Also, if you need to manage both text and other data at the same time, it's better to put them all in a database, so you get the database guarantees on transaction management and concurrency control. On the other hand, standalone full-text search libraries like Lucene usually provide more features and are easier to customize. So which type of FTS implementation to choose usually depends on the needs of the application. In this lesson, we'll cover full-text search functionality in PostgreSQL. Here's the documentation about FTS in PostgreSQL. Postgres' documentation is very well written, so check this one out when you have time. Now let's try doing full-text search in Postgres. But before we do some queries, the first thing we want to check is the text search configuration in Postgres. This configuration is very important as it determines how things like tokenization, stop words removal, and stemming are performed. So there are a few commands that you can use. For example, there's this /df command, and this command shows all the text search configurations that are currently supported by the database system. As we can see, most of the Western languages are supported. Unfortunately, there are no Asian languages here, but we are going to use English, so we are okay. And then another command is this one, show default text search config. And it says English, and English is one we want, so we are okay. And if the configuration is not what you want, you can use set default text search config to set it to whatever language that's supported. And also you can set the default search configuration in a configuration file, and there's a data folder and there's a PostgreSQL folder. Okay, so we check text search configuration is English and it's okay, and then we can do something with it. So we're going to use an example to illustrate the full text search functions in Postgres, and this is the schema we're going to use. So we're going to use a table called messages. It has 4 columns: ID, subject, content, author. ID is of 0 type. 0 is basically integer with auto increment, and in Postgres that basically means this column, this ID column will draw new values from ID sequence. So this is why we have a sequence here. But in any case, it's just an integer column with auto increment, and we have subject, content, and author. And content is a text type. So you can think of a text type like a very, very, very large varchar type. So this text type support, if I remember correctly, text up to, I think, 4 gigabytes or 8 gigabytes or something like that. So it's essentially a very large varchar, which can be used to store like long articles or documents and so on. So here I have already created the tables, and in fact I have already put some data in it. So if we do a select star from messages, we can see that I have 3 records in it. One record says today's weather, it's a very cold day. Second one says computer book sale, I'm selling some books. And third one says hello world. Hello world is computer program, something like this. Okay, so we want to do full text search in PostgreSQL, and fortunately for us, it's actually pretty easy to do. The reason, as I mentioned, is that full text search functionality is implemented as an extension to SQL, and this extension actually doesn't include a whole lot. It includes only 1 new operator, 2 new data types, and a few functions. Here are the 2 data types, TS vector, TS query, and to perform full text search in PostgreSQL, the data must be converted to the TS vector type, and the query must be converted to the TS query type. And these 3 functions can be used to do the conversion. So let's see a few quick examples. So let's say we do a select to TS vector, and we can give it a string. Let's say what title? So these are some really good apples. Okay, so take a look at this and see what 2ts vector does. So notice that originally the sentence is these are some really good apples, and after converting it to ts vector, we get APPL, we get good, and we get really. So what this means is, if you remember what we talked about, this 2ts vector actually does tokenization, stop words removal, and stemming. So words like are and some are actually removed, and these are also removed. And words like really, good, and apples are stamped, and I'm actually not quite sure whether the stem of apples is APPL, but I'll take whatever PostgreSQL give me. And we can try a few others, like the final will be Monday or Sunday. And we can see that again, the stop words like the, will, be, on are removed, and we are left with final, Monday, and Sunday. Notice that the numbers here are the positions of the terms in the original sentence. So final is the second word, Monday is 1, 2, 3, 4, 5, 6 is the sixth word, Sunday is the eighth word, and so on. So this is what 2ts vector does, and we can also do something like 2ts vector content from, let's select content, and 2ts vector content from messages, and we can see that the original content is it is very cold today, and after converting to ts vector it becomes cold and today, and I'm selling some computer programming books, and after stemming it becomes book, cheap, compute, and pretty program sell. Something like this. So this is what 2ts vector does, and 2ts query and plain 2ts query do something similar, except that they convert strings to a ts query instead of to ts vector. If you use 2ts query, you can use logical operators and or and not to construct fairly complex queries. For example, you can write a query that looks like this, which means the results of the query should include all three words, full, and text, and search. Now, if you write a query like this, it means the results should contain the words full and text, or the results can contain the word search. And you can write something like this, which basically says the results should either contain the word search or contain the word full, but not the word text, and so on. And in practice, though, you probably will mostly use plain 2ts query because queries are usually provided by users, and most users are probably not sophisticated enough to write queries like this, and most likely the users will simply enter, some words like full text search, and what plain 2ts query does is it will convert this query into something into this query. In other words, it will assume that all the query terms need to appear in the results. So we can, let's quickly do an example. For example, we can say 2ts plain 2ts query Java books, and we can see that it converts this into this query Java and book. Notice that again, similar to again, similar to 2TS query, it does stemming, stop words removal, and so on. So it actually removed off, but kept lots, and then stemmed lots into lot, and books into book. And this will become a query that requires all three words. Now, if you do 2TS query, however, you'll get an error because 2TS query require that those logical operators to be explicitly included in the query. So if we want to do 2TS query, you'll have to say lot and something like this, and still it will drop off, and that does stemming and all that. Okay, so once we have TS vector and the TS query, we can perform search using the match operator at. The match operator returns true if the TS vector is a result for the TS query, and returns false otherwise. The operator can be used in several different ways. We can say TS vector match TS query, or TS query match TS vector. We can also say text matches TS query, and this is equivalent to vector query. And we can say text match text, and this is equivalent to vector and query. The thing that you need to be careful here is that for whatever reason, the match operator does not support the form query match text, which is kind of odd because other forms are kind of symmetric. For example, we have vector query, query vector, we have text query, text text, and you would expect there's a query text form that is supported, but query text form is in fact not supported for whatever reason. And here you need to be careful, because if you accidentally use this form, you won't get an error message, but the results may be wrong. So it could create a problem that is very hard to debug. Okay, so now we know enough about FTS in PostgreSQL, so we can do some queries. And let's do a couple of queries here. And let's go back to the, oops. Let's go back to the database. And the two queries we want to write are find the messages that contain the phrase computer programs in the content, and then we want to find the messages that contain computer programs in either subject or content. Okay, so again, this is what our messages table looks like. We have ID, subject, content, and other. So if we want to look for messages that contain computer program in the content, we can say something like this. We can say select star from messages where plain 2TS query computer programs matches 2TS vector content. So notice that this is how we use a match operator, and we convert query string into a TS query, and we convert the content column to TS vector and perform a match. And if it's a match, the result should should show here, and in fact we get the correct result, computer program, and because of the stemming, computer programming and computer program will match computer programs. So as we can see, by and large, it's really easy to do full text search in databases because the syntax is still SQL, and you still have your select something from table or some condition syntax, and all we need to do is to use a couple of new data types, a few new functions, and new operator like this match operator, and that's more or less it. Now, let's do this query. This one says, find the messages that contain computer programs in either the subject or the content. So it's more or less the same query. And we can say, plain 2ts query 2ts vector subject or content. And right, so this works again. It returns the same results because because these are the two only records. This example shows that, again, it's still SQL. If you want to have more than one condition, you can have more than one condition, and all you need to do is, use and or not and those logical operators. However, I want to do a little bit more about do a little bit more with this example. So notice that if we look at this query, we notice that we have to do plain 2ts query twice here. And not only it's kind of tedious to write, it also not good for performance because converting something to a TS query, as we know from learning all those steps in the processing, is fairly expensive. We probably don't want to do this multiple times unnecessarily. So there's a nice trick we can use. We can do something like this. We can say select m.star from messages m. So m is the alias for the messages table, and we can say plain 2ts query computer programs q, where. So notice that we put this query here and we use it as a pseudo table, and the good thing about that is then later on we can simply refer that query using its alias instead of writing plain 2ts query many times. And here we can see then q matches 2ts vector subject or q match 2ts vector content, and it still works. This is a nice little trick that we can do with the SQL syntax of PostgreSQL. And there's yet another way to do this query. So here, notice that we are doing 2ts vector, and then we are doing the matching twice. So another way to do this is to do the matching only once, and It's something like this. And let's run it, make sure the syntax is correct. Yes, it's correct. So this operator, this double bar, unlike in Java, double bar means or, but the double bar in PostgreSQL means concatenation. So what we're doing is we're actually concatenating two TS vectors into one, so that when we do matching, we can simply take the query and try to match the concatenated TS vector. If you want to take a look what the concatenated TS vector looks like, it's something like this. We say to TS vector, and let's say we concatenate hello world with how are you doing? Let's try, this is a test. Okay. Well, apparently stop words removal would remove both you and do. That is somewhat surprising. Let's say another one, CS520 videos. Okay, so as you can see, this is how TS vector concatenation works. It simply becomes one TS vector. Yeah, I guess the surprise here is that how are you doing all considered stop words. Anyway, for this query, there are three ways to do it, and later on we'll use this trick with the query quite often, so get comfortable with this syntax. Okay, so we know how to do queries by converting query to TS query and converting data to TS vector. The problem, however, is that doing query like this is very, very inefficient. The problem is for every query, we have to first process every record to convert them into TS vector, and then we have to check every record and see if it matches the query. So you may be wondering, where is that index thing, right? And we can, of course, create an index to speed up the process. And because we're using a database system, the syntax of creating an index is very similar to creating other indexes in a database. We can basically say something like this. We can say create index, and then the name of the index, and then say on the name of the table, and say using, and the index type, and the index type is gene. There are actually two full-text search index types in PostgreSQL. One is called gene, and the other one is called gist. There are some subtle differences, but by and large, gene is a more general purpose index. So when in doubt, just use gene. Now, gene index has to be created on a TS vector type, and our content column is text type. So we have to convert that content column into a TS vector and then build a gene index on top of that. Now, this kind of thing, index is known as an expression index or function index, meaning that the index is not built on a column, but on the results of applying an expression or function to the column. Generally speaking, you need to be careful when you use an expression index, because in order to utilize the index, the query must have the exact expression in it. The recommended way to do full-text search in PostgreSQL is to use a separate TS vector column, so we can build a regular index for the column instead of using an expression index. Another advantage of using a TS vector column is that we can combine all the columns that need to be searched into one, so they can be searched all at once. Let's see how we can do that in our example. So we'll first add a column to the table which is of the TS vector type. So add a column, we can say alter table messages, add column, and the name of the column I'll call it TSV, and the type of the column is of course TS vector. So if we do that, messages, we can see that now we have an additional column here, but that column is currently empty. So to populate that column, we can say update messages, set TSV is, and we're going to set the TSV column to be the combined TS vector of both subject and content, so that we can later on just simply search the TSV column to search both subject and content. So this should do it. And if we do a select again, we can see that now that column has the TS vector of a combined TS vector of subject and content. And with that column, then our previous query becomes simply select star from messages, where plain to TS query, matches TSV. Right. Okay, so this column is useful for full text search purpose, but note that it is also the only purpose of this column. In other words, we just need this column to do full text search, but this column, we would not want to include this column in our data model, for example, because it's of no use in application code. But then the question is, how do we update this column if the application cannot even see this column? If this column is not, for example, included in the data model class and mapped by annotation and all that. The answer is that we can use a trigger to update this column automatically whenever the rest of the record is updated. A trigger looks A trigger looks like this. Database triggers and trigger functions are something covered in classes like CS 422. Here we are not going to go into any details. You'll just need to be able to understand this code and then do some copy and paste and some simple modifications. So this is how we can create a so-called trigger in database. We can say create trigger and give it a name, and then this trigger needs to be created for a particular table, and we say this trigger is created on the table messages, and this trigger is going to be triggered or so-called fired when certain event happens on this table. And here the events are insert and update. And once an insert or update happens on this table, then for each row affected by that insert or update operation, we execute a function. So this is essentially what a trigger does. It waits for, well, you can think of it as event handlers essentially. Events are events like insert and update and delete, and if those events happen on a particular table, and then it executes some code, and here it's called a trigger function, but we are more familiar with the term event handler. You can think of this as a callback function or something like that. Now, that function is created here using the create or replace function statement. And again, to understand all the details, we need to know a little bit about PL, PostgreSQL, those type of procedural language, which we won't get into. But like I said, you don't really need to know all the details if you don't want to, as long as you can kind of read the code and understand what it does. So what this one does is this new represents the new record to be inserted or updated into the table, and the new.tsv is a TSV column of the new record. So when a user inserts a new record into the table, that TSV column is presumably empty. So what this trigger function does is it will populate that TSV column of the new record by taking the subject column of the new record, convert it into a TS vector, and then take the content column of the new record and convert it into a TS vector, concatenate them together, and assign it to the TSV column. So in other words, this function will populate the TSV column for us, and then this trigger function will return the new record, and the new record will be updated or inserted into the table. So let's grab all that code and let's run it here. So this would create a trigger on the messages table. So let's insert a new record just to see how this thing looks like. We'll say insert into messages, and we'll give it a subject, a content, an order, and the ID field will be automatically populated by the auto increment sequence, and the TSV column will hopefully be populated by our trigger. So we'll say values and subject. Let's say subject is what's subject? Let's say subject is this is a test, and content is today's weather is too hot, and order is see or so. Okay, it's inserted, and if we look at the the table, we can see that this entry is indeed inserted. It automatically takes a ID value of 4, and also notice that the TSV column is automatically populated by the trigger, and it says hot test today and weather, and the weather apparently is misspelled. Okay, so this is how we can create a TS vector column and then automatically populate it, and this column is of course good for text search queries, and of course on top of that we can now create an index on this column, and it's no longer an expression index. So let's do that. This will create a column index on that TSV column. Yes, and then full text search can now utilize the index, which is great. Okay, that's mostly it regarding the functions, operators, and data types related to full text search in PostgreSQL. But there are 3 more functions which are quite useful. So here we are. The first function is called setWeight, and it gives a weight to a TS vector, and those weights are represented by 4 different characters, and the character A represents weight 1.0, character B represents weight 0.4, and so on. So these weights, the purpose of assigning weights is they can be used later when the relevancy score is calculated. For example, typically we want to say that if a word is found in subject, it should be considered more significant than if the same word is found in content. So if we want to express that, we can give the subject field a weight of A and the content field a weight of D. So if a query term is found in subject, the relevancy score will be higher than if the query term is found in the content. The TS rank returns the relevancy score, and TS headline highlights the query terms in the results. Something like this. For example, if we search for web development, and we can see that web development, those query terms are highlighted in the search results. For example, here and here, and yeah, for whatever reason, they all appear in the URL. Well, apparently, if they appear in URL, they are considered. Yeah, here is another one. Notice that this one is bolded, and this one is bolded. So basically, TS headline would highlight the query in text, query terms in text. So let's try this. So for example, let's say yeah, let's do this. Let's take this one. And let's change this to set weight to TS vector subject A. So we're going to give subject a weight of A, and we are going to give content a weight of D. Okay, so then let's rerun this. Let's rerun this query. Which one? Let's rerun this query. And let's change this to subject content from messages M and plain to TS. Query Q, where Q matches TSV. We also want to use TS rank to check the relevancy scores of the results. So TS rank is TS vector TS query. So TS rank is TS vector query and subject content, and something like this. Let's try this. Okay, so we can see now that we still have the same two records, but the first one has a relevancy score of 0.15, and the other one has a relevancy score of 0.099. So why is the first one considered more relevant? Well, because we are looking for computer programs, and we have a match in the subject that matches computer, right? And in the second record, there's no computer or programming subject, and it's only matched in the content. Remember that we have a given subject a higher weight, and that leads to a higher relevancy score, which is probably what we want, because after all, subject is considered more important. And this is what set weight does, and this is what TS rank does. And if you are implementing your own search engine, for example, you probably would want to order your results by the TS rank, so that the more relevant results are listed first. Now, we can also use TS headline to highlight the query terms, and the function takes a text and then TS query. So we say TS headline, text is subject, TS query is Q, TS headline content, and then Q. So if we run this, we can see that by highlighting, it basically puts bold tag around the query terms. So computer will be bolded, computer programming will be bolded, computer program will be bolded, and it will basically create a display that's similar to Google search results. Okay. So at this point, we pretty much know everything about doing full text search in SQL, but we still know how to do this using Hibernate and JPA. Because full text search is not a standard SQL feature, the Hibernate query language or the JPA query language does not support FTS, which means we have to use SQL directly. And fortunately, this is fairly easy to do using the create native query method in Entity Manager. Notice that here we are using an SQL query. This is an SQL query, select from tables, columns, and so on. This is not an HQL or JPQL query, but we can still take advantage of the other capabilities of the Entity Manager. For example, we can still set parameter, and we can still get the if the query returns the right columns, we can still get the results as objects instead of rows and columns. And another way to do this is to use named query. A named query is really just a query with a name, and in JPA, a named query can be either a native SQL query or JPQL query, and the Entity Manager is smart enough to figure out which is which. You can specify a named query using a named query annotation like this, but personally, I don't like writing queries in annotations because they look really messy, particularly complex queries. A better way is to put the named queries in a Hibernate mapping file that looks like this. So let's take a look at the named queries in CSS2. It's here. So you can put it in a Hibernate mapping file. The name of the file is not really important. Of course, it should have the XML suffix because it's an XML file. But whether you call it namedQuery.hbm or whether you call it ABCD, it doesn't really matter that much. You just need to put this file somewhere under the class path, or in Maven directory structure, it should be under main resources, and then Hibernate will find it. The content of the file looks like this. You can it starts with XML DTD, and then there's a Hibernate mapping element, and then you can put in any number of named queries using the SQL query tag. For each query, you need to specify a name, and then you need to specify a return class, which is a type of objects returned by the query, and then you can write out the query inside character data brackets that looks like this. If you are not familiar with XML syntax, it doesn't really matter. All you need to do is copy and paste some example like this, and then just create your own SQL query following the by changing the query part of the code. So once we create named query like this and put it in a Hibernate mapping file, place it somewhere under class path, and then in our DAO code, we can then call those named queries by saying create named query, and then specify the name of the query, like the name here, and then we can also set parameters and so on, and get the results just like other query, query types in entity manager. In CSS2, there are many places that use full text search. Search courses by code and name is probably the simplest example. So let's take a look at that and see how the whole thing is put together. The queries, the course search function is here. If you go to department courses and click on courses, you'll see a search box here. Here you can search, you can perform a full text search on the course name. For example, if we want to find all the database courses, we can search for database, and it will list databases. If I want to search for algorithm course, Java course, really? Nothing has Java in the title, then maybe programming language. What's CS201 is called? Introduction to Programming. Oh, it's just programming, right? Not language. Really? Oh, there are programming languages. Programming language. Okay. Anyway, you get the idea. So this is a full text search, simple full text search example. We put in a query, we click search, and then the results will be shown and displaying the code name and the coordinator of the course. So if we look at the data model, the data model is here, course. Right? Each course has an ID, department code, name, number of units, coordinator, description, and so on and so forth. So the model class, of course, is going to be mapped to a database table, which looks like where is it? Let's search for it, which looks like this: ID, department ID, code name, and so on and so forth. So note that just like in our example, we did alter table add column TSV and added a TS vector column. And also notice that this TSV column is not part of the data model. So our application code doesn't really need to care about how full text search is going to be performed. So the TSA column is not included in the data model. Then how is this TSA column updated? Well, it's updated by this trigger, just like the trigger we've seen. We set the weight to weight A to the code or part, and then weight B to the name part. And so when we perform a search, the search is performed in the controller. So the controller will take a string term and it will call the DAO method called search. And the DAO method is here, search courses. It takes a search term, and it also takes a second parameter called max results. If this max results is a negative number, it means no limitation. Or if, for example, you only want the top 20 or top 40 results, you can specify 20 or 40 here. And here I specified -1, meaning that I want all the results, no limit. And so if you look at the actual implementation, it created a named query called course search, and it returns course objects, and it sets the term parameter and gets the results. And the course search named query is in here, and in fact it's the first one. You can see that it does a select star from courses where obsolete is false, so this course is not obsolete yet. And there are actually two conditions in the where clause. The first one is plain to TS query matches TSV, so there's a full text search condition here, or it also have an additional condition that does code like the query term and then the wildcard symbol. So what this one does is it performs a prefix search of the course code. So in other words, we can try something like CS122, and this will give us all the courses that has the CS122 as a prefix of the code. So CS122, 122.0, 122.2, and so on. So what this means is that full text search capability is just part of the SQL, extended SQL. So you can use it to do just full text search, or you can use it to use it as part of a query like here. It's all up to you depending on what you need for the query. Okay, so this is how everything is put together in a web application using Hibernate and JPA, and underneath it uses full text search support from a database management system. And that is the end of this lesson.